Alright, so we're going to go through problems 21 through 25 of the 2008 GRE. Sorry it's moving a little slow. I got some stuff going on and just being busy, but I still want to grind through these. Real quick, please subscribe if you're not already. It helps me out. And please like this video. If you can do that for me, that would be awesome. And in exchange, I will do everything I can to make this make as much sense as possible. Okay, so the first one says, for an adiabatic process involving an ideal gas having volume V and temperature T, which of the following is constant, where gamma is Cp over Cv? Okay, so we need to, I'll do this one over here. So this requires the first law of thermodynamics. Now our first law of thermodynamics tells us du equals dq plus dw. And sorry if I'm going a little slow with this. I'm really not sure what you should be expected to memorize exactly yet. I'm kind of going through that process on my own now. Maybe I can share the LaTeX doc that I have for the equations. So I just went ahead and derived this. It seems a little long for a derivation, but okay. So du, that is your internal energy. This is your internal energy. I'll call it IE. This is your heat. And this is the work done on the system. Some books it's the work done by the system. It's just going to depend on the whichever way they choose to do it. It doesn't really matter. It's just a convention, and the sign will change. Now, for an adiabatic process, that means there's no dq. There's no exchange of heat. So this is 0. So our first law of thermodynamics says that du equals dw. dw, well, I'll go ahead and kind of show it here. Let's say we have this container. Let's say we have this. And then, so it's kind of like this little piston. And in here is your gas. That is going to push the piston up, and it's going to have some change in volume, which we'll call dV. Now work is equal to force times the displacement. Now work, though, we can also say is pressure times area times dx. It's a pressure. Just rewriting our force as that. But area times a little bit of dx, that's just dv. And by convention, because of how we're defining work, it's a minus pdv. Because we're defining our work to be the work done on the system, not the work done by the system. So in this case, it would be negative. It's just a convention, though. It kind of depends on where you're doing it. So with that in mind, du is now p dv. It mentions it's an ideal gas. So for ideal gases, U, your internal energy, is equal to 3/2 RT. Okay? So if we take the derivative of U with respect to temperature, maintaining a constant V, well, that's a pretty easy derivative. That's just going to be 3/2 R. And this is your heat capacity at constant volume. This is the definition of your heat capacity, and we're keeping it at constant volume. So that's what that is. In other words, du equals Cv dt, if you can imagine multiplying over our differentials. Well, then we can take this and plug it into here. So we have CV dt equals negative P dV. But again, it's an ideal gas, and we know for an ideal gas, PV equals RT. It's actually nRT, but just to simplify it here. Which means that your pressure then is RT over V. And this can now be plugged into here. So, okay, it's taking a little bit of room, but it's okay. CV dt equals negative RT over V dV. Rearranging this, we can divide by the T and all that stuff. So I'm getting my T's and V's onto one side. I'm dividing over by CV as well. Okay. And then what can we do is we can integrate both sides. Those are constants with respect to the integral, so that can just be factored out. And you'll get ln T2 divided by T1 equals minus R. I'm sorry, there's no longer a T there. Move that over. It's about to say divided by CV is the natural log of V2 over V1. Just doing our integration there. Okay. Now, Cp minus Cv, so this is your heat capacity. So up here is our heat capacity with constant volume. Cp is with constant pressure. So you're just holding pressure constant, you're holding volume constant there. This is equal to minus du dt at constant V plus du dv at constant t plus p dv dt at constant p. And then you have your minus du dt at constant v. So this part is this, and this guy is here. And you can see that these will basically just get rid of each other. So that's just the definition of Cp and Cv. And if we do that, like I said, that stuff goes away. You get Cu Cv constant T plus P dV dt at constant P. Now, du dV at constant T is equal to 0. And we can see that if we go back to our equation. It's, if you take the derivative of that with respect to V, it's going to be 0. Okay? And at the same time, V is equal to RT divided by P. So if we want to find dV dt at constant P, in other words, we want to find this guy because that's the other part of it, you just have to take the derivative of V with respect to T, and you can get R over P. So then this can be plugged into here. So Cp minus Cv equals P times R over P, or just R, because these obviously drop. Okay? Which means Cp equals R plus Cv if we add Cv to both sides. Okay. Now we can divide both sides by, or everything by Cv. This is the definition of gamma. Okay. And then we're going to have just R over Cv plus 1. Okay. So gamma minus 1 is R over Cv. And again, if we look, there's a negative here, but it's essentially the exact same thing. So we can plug that in. So So plugging that into the equation, the natural log of T2 over T1 equals 1 minus gamma. There's a negative out front, so it changes the sign. ln V2 over V1. We could also do gamma minus 1 times a negative. That's actually what I'm going to do because, so I'll show you here. We can use our properties of logs. These can go into the exponents, as can let me do a different color, as can this guy, whatever's out front of our log. Now, if we plug the negative up there, that's just going to flip the order. So that's going to make that V1 over V2. And then we have our gamma minus 1 up there. Okay? That's all that's doing is flipping the order. And now I can raise everything to the base E to get T2 over T1 equals V1 over V2 gamma minus 1. Or T2 V2 gamma minus 1, if I just cross multiply here, equals T1 V1 gamma minus 1. And notice that this is just a constant. Okay. And we also know, since there's a constant there, we're just going to worry about the proportionality. PV is proportional to T. We're not worried about the R because that can be taken in by the constant. So we can just worry about the proportion there. So if that's the case, I can say, I can plug that in here. So for example, we can have PV V gamma minus 1 equals PV V gamma minus 1, or just a constant, or PV gamma equals a constant. Let me get back to the question. 21. Okay, so theirs is in terms of T. I went a little bit too far here, sorry. So we can just say TV gamma minus 1. Which one is that? TV gamma minus 1. Option choice C. So I kind of went off a little bit there. I'm going to go a little bit faster on the other ones to make up for it. But anyways, 22. An electron has total mass energy equal to 4 times its rest energy. The momentum of the electron is, so the equation we'll use is, you can see it here, but I'm going to write it down over here. In fact, let me see if I can do this. Yeah, let's give us a second chance here. Okay. So the equation we're going to use is E squared equals MC squared squared plus PC squared. And it mentions that E is equal to 4 times the rest energy. The rest energy is MC squared. So then we have 4 MC squared squared equals MC squared squared plus PC squared. So we have 16 m squared c to the 4th minus m squared c to the 4th equals p squared c squared. 15 m squared c to the 4th equals pc squared, p squared c squared. Let's see, that can divide out. Okay, and you square both sides, you're going to get mc, the square root of 15, is equal to your momentum squared. There we go. No, not squared. I already divided. Okay. So that is this option here. Looks like option C. Okay. 23 is two spaceships approach Earth with equal speeds as measured by an observer on Earth, but in opposite directions. A meter stick on one of the ships measures 60 centimeters. Okay. So what we're going to do here, I'll do this over here. So this was 22. This can be 23. We can use our length contraction formula here. Right? And we can find our V this way. So L squared divided by L naught squared equals 1 minus V squared over C squared. 1 minus L squared over L naught squared square root C equals V. So just solving for V. And if you plug this in, you'll get 80% the speed of light. But let's read the question. So two spaceships approach Earth with equal speeds as measured by an observer on Earth, but from the opposite directions. A meter stick on one of the spaceships measures 60 centimeters long by an occupant on the other spaceship. What is the speed of each ship as measured from Earth? So the problem with this being, this isn't our answer. And the reason being is because we're measuring this from the perspective of that ship moving. So if you have these two ships moving towards each other, that's not necessarily going to be the speed a stationary observer measures. Well, how do we do that? Well, we have an equation. V equals V prime minus U over 1 plus V prime U over C squared. This, we know, that's what is measured by the other moving observer. And V prime and U are really the same thing, just in opposite directions. So V prime equals minus U. It mentions they're moving at the same speed, but they're coming in opposite directions, so there's a sign difference there. So then V equals minus 2U over 1 plus U squared over C squared, making that little substitution. Okay, and then plugging in our values and multiplying over, we'll get minus 0.80 minus 0.80 U squared plus 2U equals 0. You can divide out a little bit and you'll get, so if I divide everything by negative 0.08, you'll get U squared minus 2.5 U plus 1 equals 0. And you could either try to factor this if you wanted to, or you could do the quadratic. I just plugged in my calculator. You'll obviously get two answers. It's a quadratic. You could get U equal 2 or U equals 0.5. This answer is nonsense. You can't get a number bigger than 1 for U. Otherwise, it would imply it's moving faster than the speed of light. So for that reason, the answer is 0.5. Okay, so that's that guy. All right, so as for the next one, 24. A meter stick with a speed of 0.8 c moves past an observer in an observer's reference frame. How long does it take for the stick to pass? So we can do L equals L naught, the square root of 1 minus V squared over C squared. We know what L naught is. That's going to be just 1. It's 1 because it mentions it's a meter stick, and a meter stick is 1 meter long. I actually have to plug this in. So let's see. This will be 1 minus 0.8 squared. I actually don't think I have that number, so let me do it really quick. Square root of 1 minus 0.8 squared is equal to 0.6 meters. So that's the length that we would see from our perspective. It's contracted, which makes sense. We would expect it to be. Then if we want to actually measure it, we could use just distance equals rate times time, where time is our distance L and our speed V, which we have. So L we just found, and then 0.8 times 3 times 10 raised to the 8th. And when you do that, you get about 2.5 times 10 to the negative 9 seconds, for answer choice B. So that's that. Question 25. There actually isn't too much explaining here. It's just a property. Consider the set wave function psi sub x, or psi sub ix, which of the following conditions guarantees the functions are normalizable and mutually orthogonal. So for it to be normalizable, what that means is the integral over all space. Let me do this down here. This will be the last one because some of those problems took a little bit more time, and I was kind of rushing through it too, so that's why we're only doing these. So to be normalizable, what that means is the integral over all space of whatever it is we have, in this case it's our wave function, needs to be equal to 1, which makes sense. You should find you should find it somewhere. If we think of psi as being related to probability. But for it to be orthonormal, it's where we're using the Kronecker delta there. Now I've talked about that one in previous videos if you're interested. But basically what that's doing, or it's I think it's actually a direct delta function, actually, not the Kronecker delta. They're similar. But what that's doing is saying our wave function is exploding at one point. Yes, it does equal 1, but only at one point. So I've talked about the delta function as well before, but you might have a graph that does this, and that's not even perfect, but basically you have a peak is what I'm trying to display. So E is the one that does that because that's what the Kronecker, or not the Kronecker delta, the Dirac delta function does. All of this stuff is equal to 0 everywhere with the exception of one point where it blows up. So answer choice E. Alright, so I went kind of fast, but I'm trying to keep these at a decent time. We are a quarter of the way done, so that's good. Sorry if I got a little bit too heavy into proving stuff that didn't necessarily need to be proved, but at least now we have it. And again, if you wouldn't mind please subscribing and liking the video, I'd really appreciate it. Thanks.